The reason why some sounds are louder than others is because sounds can have different levels of intensity. And technically, sound intensity refers to how much power that sound is producing and spreading over each unit of area. Or in other words, how many watts of power are being transmitted and spread over a square meter of area. So the technical measurement for sound intensity is in watts per meter squared. The intensity of a sound ends up depending on how much power is behind the source itself and how far we are away from the source. And we can relate this to what we know about water waves. So imagine the water waves that are created when I drop a rock in a pond. If I drop a larger rock, which represents an increased power source, that's going to create waves with greater intensity. But if I get farther away from that original point where the rock went into the water, we notice that the size of the waves massively decreases. So we lose a lot of the intensity of our waves as we get farther away from the source, as we have increased distance away from the original source, because the energy is spreading out. When we want to actually measure intensity, it becomes actually very tricky to measure it in watts per meter squared. Because when we measure things only in watts per meter squared, we have some everyday sounds that are incredibly tiny numbers and other everyday sounds that are billions or trillions of times louder than that. So we actually develop a slightly different scale. Instead of measuring everything in watts per meter squared, we connect this to a new kind of unit called bells. And we just spell it B-E-L and use a capital B to represent it. It's actually named after Alexander Graham Bell, the inventor of the telephone. But even a little bit more commonly than that, we found it's useful to take each bell and subdivide that into 10 separate pieces. And when we take a unit and we split it up into 10 pieces, we get a decibel. Just like a tenth of a meter is technically a decimeter. So we get a decibel, and we use a lowercase d and an uppercase B to represent it. That's 1/10 of a bell. To understand what bells and decibels really mean, we first need to kind of understand how watts per meter squared connects to decibels. The threshold of hearing means the quietest sound on average that most humans are able to hear. And what we found through various experiments is that that's about 10 to the minus 12 watts per meter squared. So an incredibly tiny number, about 1/trillionth of a watt per meter squared. And because that's the quietest sound that humans can hear, this decibel range has to do with how humans hear these sounds. And so we use that quietest possible sound and we calibrate it as 0. So we start our decibel scale at that quietest possible level. So 0 bells, which is also 0 decibels, or decibels, is actually 10 to the minus 12 watts per meter squared. From there, though, the decibel scale and the watts per meter squared version of the scale, they relate to each other not in a linear way, but in a logarithmic way, which means that every time we have 10 times more intense of a sound, so every time our sound gets 10 times more intense, we increase our bells by 1. Or in other words, we increase our decibels by 10. If a sound is 100 times more intense, that means we increase the scale by 2 bells, or 20 decibels. 1,000 times more intense, just 3 bells, or 30 decibels. So every time the sound gets 10 times louder, we add an additional 1 bell, which really means we add an additional 10 decibels to the previous level. So here are some examples of things that we might see in our everyday lives. Again, the threshold of hearing, the quietest sound we can hear, we call 0 decibels, and that's 10 to the minus 12 watts per meter squared. A whisper might be something like 20 decibels, which you'll see if we just compare the values in the watts per meter squared category, we have to multiply by 100, or in other words, 10 to the power of 2, in order to get from 10 to the minus 12 to 10 to the minus 10. And so in going from the threshold of hearing to a whisper, we've got a sound that's actually 100 times more intense, which means that it's increased on the decibel scale by 20 decibels, or 2 bells. You can see some other examples on there. Some very loud things, like a rock concert, are about 120 decibels. The threshold of pain is right at that level where most humans on average tend to start experiencing physical pain and distress. It starts to do some damage to your eardrums when they vibrate that intensely. And that's why rock concerts can tend to cause people a little bit of ear pain, because right near there is that threshold of pain. So a rock concert is about 120, and the threshold of pain occurs at about 130. Military jets taking off are something along the lines of about 140. And so that's why, of course, people that work around those settings need to wear proper ear protection. And lots of people in intense noise environments need to wear ear protection. Something around 160 decibels, and regardless of the situation, you're almost doing instant damage to your eardrum, regardless of how much exposure you have. I want to just take a little bit of time and talk a little bit more about this decibel scale, though. So I'm going to add a little bit to your note here and just ask a simple question that'll hopefully allow us to work with this decibel scale a little bit easier. So the question I want to ask is, how do the following sounds compare to a 10 decibel sound? So if we were to start with a 10 decibel sound and then hear some other sounds after that, let's try and see how we can compare them and how many times more intense each one would be. So let's say the first little example I'm going to talk about is, what about if we had 30 decibels? Well, what does that tell us? Well, a quick little calculation tells us that we have a difference, which I'll just put a short form of diff for difference. We have a difference of 20 decibels, because we went from 10 to 30, so we have a difference of 20 decibels. But remember, 20 decibels is really 2 bells. And each time we go up by 1 bell, we go up by 1 power of 10. So going up by 2 bells, or 20 decibels, is like going up by 2 powers of 10. So really this is like 10 to the power of 2, or in other words, 100 times more intense. Or in other words, 100 times louder, assuming that it's at a frequency that we can actually hear. So if we go from 10 decibels to 30 decibels, it's because we've played a sound that is 100 times louder. That's how the scale works. Another example, what about if I had 110 decibels? So a very loud sound now. Well, comparing that back to 10 decibels, now it's a difference of 100 decibels. Or in other words, remember, that's 10 bells. So every time we went up by 1 bell, we increased the power of 10 by 1. So this is 10 to the power of 10, which actually equals 10 billion times more intense. And I'll just try one other. And we'll be taking these up in a bit more detail in class and going through them again. So don't worry so much if it's still a little bit confusing. But the last one I'm going to look at is 55 decibels. So imagine I have a sound now that's 55 decibels and I want to compare it to a 10 decibel sound. Well, again, if I find just the difference in decibels, it's now a difference of 45 decibels. Which is actually, strangely, 4.5 bells, or 4.5 bells. And remember, every time we go up by 1 bell, we're increasing by 1 power of 10. So in this case, if we want to say how many times louder it is, or how many times more intense, it's 10 to the power of 4.5, which seems strange, but there's no reason why we can't do an exponent that's a decimal. And in fact, your calculator can handle this just fine. And so when your calculator churns that out, you'll get something along the lines of 31,622 0.7 and a bunch of decimals after that. So that's how many times more intense sound would be in this case. About just under 32,000 times more intense. Because again, 10 to the power of 4 would be 10,000, and 10 to the power of 5 would be 100,000. So we got something that's kind of in between 10,000 and 100,000. Not exactly in between, but somewhere in between. And it works out to about 31.6 thousand times more intense. That's the basic idea, but as I said, if this is still a little bit fuzzy for you right now, we're going to revisit these examples in class and talk about it in a bit more detail.